Okay, and so now we're going to talk about the standard error of the sampling distribution of means. So the variability of a distribution of scores is measured by the standard deviation. The variability of a distribution of sampling means is measured by the standard deviation of the sample means and is called the standard error of the sampling distribution of means. And it's written like this right here. So we have the standard error of the sampling distribution of means. Kind of looks like it is the same symbol as the standard deviation, but with an M right there. So in journal articles and other texts, this might be identified as the standard error, SE, or SEM. It provides us information on how much error you should expect on average between the sampling mean and the population mean. So it's essentially the average distance between the sample mean and the population mean. This sounds a lot like standard deviation, right? Standard deviation, it's the average deviation, the average distance from a score to the population mean. This is the average distance, average deviation, average error that you can expect, average distance between a sample mean and a population mean. That's what the standard error is. Standard deviation for the distribution of sample means equals standard error. They're synonymous, same thing. So standard deviation for the distribution of sample means equals standard error. So just let that sink in for a second. Just going back to what a standard deviation is, how we've been using it thus far. We're just taking that information and extending it to a sample of means. We're no longer working with individual scores, we're working with sample means. Again, what is a standard deviation? A standard deviation is the average distance from a score to the population mean. Standard error, average distance between the sample mean and the population mean. That's why standard error is conceptualized as the standard deviation for the distribution of sample means. If you're told this is a distribution of sample means, if you're told these are sample means, you know you're working with standard error, not standard deviation in and of itself, unless you specify it as this is the standard deviation for the distribution of sample means. That's the standard error. The most accurate and precise way to refer to this concept is in terms of standard error. So the standard error of the sampling distribution of means is the standard deviation of the distribution of means. We talked about that. We went over that definitionally with this point right here. When it is large, the means are widely scattered. What am I talking about when I say means? The sample means. So again, think about what we saw with standard deviation. If we had a high standard deviation, that means there is a lot of variability. The range, scatteredness that you would witness in your distribution would be much greater. This suggests that there's a big difference from one sample to another. It's the same concept as when we talked about standard deviation. The standard error of the sampling means provides a measure of how much distance is expected on average between the sample mean and the expected value of the mean from the distribution of the sample means. The average distance, this also gives us information on the average distance between the sample mean and what other statistics, or singular, so what other statistic? The other statistic that it would provide this information on would be the population mean. Why? Because the expected value of the mean of a sample distribution, this right here, is equal to the population mean. And so, if this gives us information on the expected, on the, of how much distance is expected on average between the sample mean and the expected value of the mean of a sampling distribution, it also gives us information on the expected distance on average between sampling mean and the population mean, because this statistic is equal to population mean. That's why the mean is an unbiased statistic. So, what are factors that affect how large or small a standard error is? The first thing to think about is the law of large numbers. The larger the sample size, the more probable it is that the sample mean will be close to the population mean. Thus, standard error, will decrease. And so again, when we're talking about sample size, we're talking about how many scores are in each of your sample sizes, or each of your samples. So if you choose an N of 100, that is probably going to be a bit more of a reliable indicator than if you have an N of 1. So the standard error should be smaller if you have N, small n, of 100 versus small n of 1. And to illustrate this, when you decide that you want your sample size to be 1, the distribution of the sample means is identical to the original distribution and has the largest standard error. In fact, when n equals 1, standard deviation equals standard error. So in this instance, this is like the worst possible outcome that you could have, because essentially you're making samples, but your samples are all just comprised of 1. And this goes back to this concept we were discussing earlier, where if you have more people and you're able to get an average from them, that's probably going to be closer to the mean, to the true mean, to the population mean, than if you just have one person and take their average. And so at this stage, basically this is the worst situation, and anything up from 1 is going to decrease standard error. So this is one thing that's going to affect the magnitude of standard error. As the sample size increases, error decreases, because the mean from that sample size will be more representative and a more valid statistic when trying to take that information and extrapolate it to the population. The population variance will also play a role. So, going back to have a go back to right here. So, thinking about standard error. So, distribution of sample means for sample size. For samples of size n, we'll have a standard deviation equal to this. This is the formula for standard error. And considering that we have here standard deviation, we know that variance is going to play a role. Why? Because standard deviation is the square root of variance. You can easily compute back and forth between those two statistics. Okay, so the smaller the variance in the population, the more probable it is that the sample mean will be close to the population mean. So the smaller the variance, the smaller the variability in the population, the smaller the error. If you don't have as much of a widespread distribution and everything's pretty much really tight, close to the mean, then your standard error, your standard deviation of the sampling means will be small. And so that's the role that population variance plays. So as sample size increases, standard error decreases. They have an inverse relationship. You need to remember that. You also need to remember as population variance decreases, standard error decreases. They have a parallel relationship. One decreases, the other one decreases. One increases, the other one increases. So you could be asked a question such as standard error for a distribution increase. What might be a reason for this? Well, if the standard error increased, a reason might be that your sample size decreased. Okay? Okay, so this is a chart that really shows you how standard error and sample size relate. And so if you have a number of scores in your sample, and this is going to be standard error, so if we have n of 1, small n of 1, we see that our standard error is quite large. And we can also see that that would be the population standard deviation. As sample size increases, look what happens to our standard deviation. Drop, 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 drop. So our standard error decreases as our sample size increases. So what have we been talking about so far? We've really been talking about several unique distributions, and I think this slide does a nice job of bringing it all together. So we have our original population, our original distribution. Then we take a sample from that distribution. So we can have samples of 25. And so we can graph that and see what it looks like. This one sample has unique characteristics. It will have a mean that is going to be a little bit different. It's not going to be necessarily 100. In fact, it's 101.5 or 0.2, excuse me. The standard deviation is no longer 15. It's going to be 11.5. And so that's just one sample, though. And so this gives us some information about what we've been doing thus far. So if we take one sample in and of itself, it's not going to be too far off from the original population, but it's not going to match it perfectly. However, if we continue to sample groups of 25 over and over and over again, and we exhaust this, so we would pick all of those in a sampling distribution. This graph right here represents the distribution of sample means. We would find that our mean is going to be exactly equal to the population mean, because the mean is an unbiased statistic, and that our standard error would be equal to 3. And so these are kind of the three things we've been talking about. So we have our original data, our population data, the sample that we're drawing from that population, and then the distribution of sample means. What does that look like? Okay. Take a second and answer this, and then I'll show y'all what the answer is. So the expected value would be 60. Why? Because, as we mentioned, the distribution of sample means for samples of, it doesn't even matter the size, if you continue to resample, the expected value will be exactly equal to the population mean. Why is that? Because the mean is an unbiased statistic. Take a second to answer these. The first one is false. We talked about this. is directly related to the central limit theorem. The shape is normal only if the population is normal or n, so your sample size, is greater than or equal to 30. For the second one, so as n grows larger, the standard deviation, the standard error decreases. Okay, so at this point, it seems like we've covered everything related to sampling means, the central limit theorem, how that helps us to know information about the shape, the tendency metrics as far as the mean, and variability of sampling distributions. So we're going to take all of that information. I think that a lot of that information was really covered in like chapters 3 and 4, and the only thing that's a little new is this whole idea of sampling error, standard error, and how exactly we compute that and its role. So we're going to take what we've gone through thus far, and now we're going to apply that information and see how this all relates to z-scores and probability for sample means. So the primary use of the distribution of sample means is to find the probability of selecting a sample with an expected sample mean. So essentially, if you have a distribution, a population distribution, and the mean is 100, what is the probability of selecting a sample with a mean of 347? Well, we can use these z-scores to figure this out. So, proportions of the normal curve are used to represent probabilities. Well, why can we use this? Well, remember some of the characteristics of distribution of sampling means? One of them is as n increases and is around 30 or higher, or the distribution of the original population is normal, the distribution of the sampling means is normal. And so we can apply what we know about the theory of normality to sampling distribution. So what we can do is we can essentially compute a z-score for the sample mean and then use the unit normal table to collect information on the probability of obtaining some type of sample mean. What we have done thus far is the probability of obtaining some score. So we are taking that information and extending it to sample means. Same concept. Slight difference is going to be right here. We'll go over it. So as with finding the z-score for a particular value, a particular score, a particular x, the sign tells us whether the location is above or below the mean. So in this situation, if the sample mean has a z-score of -4, you know that it is 4 standard error units below the mean. Yeah, -4, below the mean. So the number tells the distance between the location and the mean in standard deviation, standard error units. Because we are working with sample means, we are talking about standard error units. Standard deviation of a sampling distribution is equal to standard error. So, what is the z-score formula when we're working with sample means? Well, we have the sample mean minus the population mean divided by standard error. This is standard error. The standard deviation of the population divided by the square root of n, divided by the square root of your sample size, is standard error. Okay. Because we are working with a sample of means, we focus on standard error. We can use that as a metric of what? We can use that as a metric of the average distance from the mean to the sample mean. So from the population mean to the sample mean. Sounds pretty similar to standard deviation, right? It's computed slightly differently, but the concept in and of itself is very similar. The biggest thing is that we're working with sample means here, not individual scores. So, what proportion of the sample means have a value greater than 525? You know right here that we are working with standard error, and because we're working with sample means, we think of z-scores in terms of standard error units, but the same principles apply. So for a distribution of sample means, the standard deviation of the distribution of sample means is sample error. So we represent it like this, but the same concept applies. It is the average distance of the sample mean from the mean, the population mean. So we can take this information and turn it into z-scores. What does that look like? Well, we'll do it the same way we did it before. We can use these statistics, these numbers, and place them into our formula. And what we find is that, oops, oh, sorry. Is that because our standard error is 25, our standard deviation of our distribution of sample means is 25, that 525 is equal to 1 z-score, 1 standard error unit above the mean. So, if we are interested in finding out what proportion of the sample means have a value of greater than 525, or what is the probability of obtaining a sample mean value greater than 525, we can take this information right here, go to our z-table. I don't know if I actually put the... So you would go to your z-table, which in your book, so the unit normal table, you would go to a z-score of 1. You would look to see what is the proportion in the tail right over here, and that is